So example 2, checking the normal/large sample condition. So we're going to be looking at an example here where they're trying to estimate the average GPA of students at your schools. So at your school, I can read. You randomly select 50 students and there's a histogram of the GPAs. So we can care about the shape of the GPAs in this sample. We can make assumptions for the population and what it would look like, but honestly, you can quit reading the moment you see this about your sample. You have met the normal/large sample condition because the sample size is large. That's all it takes. That's the easiest one. Well, kind of. This, in addition to saying that it's from a normally distributed population, I'd say are the two easiest ways to meet this condition. I'm also going to quantify what I mean. My sample size of 50 is at least 30. So I'm not going to do anything else here. I'm just checking that condition, but I have met it. For part B, every time. For part B, it's wanting to know how much force it takes to pull wood apart. So we have a stem plot of force required to pull a Douglas fir apart. We have 20 randomly selected pieces, so that's a problem here. So we can't just meet it as quickly as we did last time. Our sample size of 20 is less than our threshold of 30. And it doesn't say that the population is normally distributed, so the only thing we have left is to look at the distribution of the data. So if I'm looking at this, I'm looking at the shape, I see very few small numbers, and most of them are sitting over here in the lower 30s. So because of that, we can describe the stem plot as being strongly skewed. So because n equals 20 is less than 30, and the stem and leaf plot is strongly skewed left, we have to say no, we don't meet those conditions. But part C, if you're wanting to estimate SAT math score at a large high school, we have a box plot of the data. Again, we have a sample of 20. So we can't meet it the really quick and easy way. But if we look at this distribution, it is slightly skewed. This tail of the top 25% is more variable, is different than the low 25%. So that's a little bit of a concern, but it's not that concerning. It's not that varied. It's not that strongly skewed. And I know box plots are not necessarily the best thing to talk about skewness, but even though this is true, I'm just going to put the box plot is only moderately skewed. It's only slightly skewed. And I do know that there are no outliers. You remember back when we talked about box and whisker plots, we said that the outliers are always dots at the end of a distribution. This doesn't have any, so I know for sure there's no outliers. It's only slightly skewed, so even though we have a small sample size, this would pass the threshold of being able to use our t-distribution for it, because we would have a sampling distribution. A sample means it's approximately normal. Now, I know some people don't like the idea of saying, well, what's slightly skewed and what's large skewed? You can slightly quantify that by looking at the distance from the high to the median. So in this case, it would be this point to our middle, and then also from the minimum to the middle. If you calculate that and make some estimates, so that's what this one is, the box plot here, then this upper end is a distance of 150-ish. That's not right, that's 250. And the lower would be 150. So it is different. It is more spread out on the top half. However, that's not that much. It's less than twice as long as the left half. So yes, longer. If you actually look at the stem and leaf plot, the median is 319.5, so it's a number here. This distance, excuse me, is dramatically smaller than this distance. and it gets quantified down here. If you actually find those distances, half the stem plot with the smaller values is more than 5 times as long as the half of the stem plot with the larger values. So you can try and come up with some ways to not just have it like, yeah, this one's less skewed. There's not any rule of thumb for this is the best way to do it. So just assume that you're not going to get any strange, I can't tell, it's on the line. Like, it'll be one way or another. So now we can actually get to actually construct this confidence interval. So as long as your conditions are met, what do you need, Eloise? Okay. There you go. Sorry. So when the conditions are met, a C confidence interval for an unknown mean, we always say it's our statistic plus or minus our margin of error. Our statistic is our point estimate. Since we're estimating mu, we're going to put x bar here. We're going to add and subtract our multiplier, which is t star, times the standard error. Now again, we're going to have to use sample standard deviation, and we'll divide by the square root of the sample size. So this is the sample error, the standard error of the mean, x bar. Sometimes it's just called standard error. I know that on the AP formula sheet, they use, what do they use? S of x bar for this. So hopefully you still have your sheet and you can actually look for it so it makes sense to you, especially if you're taking this test, but the AP test. But let's actually create one. Example 3, a 2016 Pew Research Center study that interviewed a random sample of 1,520 American adults found that the average number of books read by the members of the sample, including those who reported reading no books at all, was an average of 12 books and a standard deviation of 18 books. We are going to construct and interpret a 95% confidence interval for the mean number of books read by all American adults in the previous 12 months. So we're going to create this interval. We have to go through our 4-step process. The first thing is we're going to state what it is we're even doing. So this set a 95% confidence interval. And then I'm going to state what parameter we're trying to capture. We are not trying to capture P anymore. We're going for mu, and I'm going to put in context what that is. That's the true mean number of books read by all American adults in the previous 12 months. So my plan is when I state what type of interval I'm going to be creating. This is called a one sample T interval because I'm only collecting one sample to use. My multiplier is going to be the T star value, so it's a T interval, not a Z interval. And it's for mu. I went ahead and wrote up the first 2 conditions because those are the ones that are really not new conditions. Excuse me. So the random condition, I'm just saying that it said somewhere that we have a random sample. So I'm just putting that, check, we met that condition. Then the 10% condition, my sample size of 1,520 American adults is less than 10% of all American adults. Same as it always has been. But then I need to look for my normal/large sample condition. So when I do this, it never said anywhere that the distribution of American adults' book reading preferences is normally distributed. So if I don't know the population is normal, then I have to look at the sample size. Well, luckily the sample size is friggin' huge, so we have a large sample. So I'm going to say just that the sample is large. And I'll quantify what I mean by that. 1,520 is at least 30. So now I can actually start doing things. As I said before though, depending on how you choose to do this, you're going to get slightly different results. So one way I'm going to do this is by the table. 1,520 is not on the table. If you actually scroll all the way back to the table, they jump from 100 to 1,000 to infinity. So the rounding down, the highest one that is available would be this 1,000. So we're going to use 1,000 as our degree of freedom, which I shouldn't have scrolled away from that because I need to use it. So I need to find the critical value. Sorry if I'm making you nauseous. For 95% confidence. So if I look in this column, in that particular row, I'll be using 1.962. Which if you happen to have the Z-star critical values, that shouldn't be that unfamiliar. When you get larger and larger samples, the t-distribution converges on the normal distribution, so they end up being approximately equal eventually. But I do need to not just assume that. Now, if I use technology, my degree of freedom would be 1,519. So then I'm going to go to my calculator, and I would like to use my inverse t distribution. I'm not going to show you what I'm doing because we already did this once. The area that I'm putting in is half of 5%, and 1519 degrees of freedom. So my calculator is spitting out 1.962. So I get the exact same thing no matter which way I do it. You will not always get the same thing. State how you get those numbers. So you don't have to do both. Whatever way you choose, note what you chose to do. So now I'm going to take that formula. I'm going to take X bar, the sample mean, and we're going to add and subtract to it 1.962 of our standard errors. And the standard error is the standard deviation of our sample divided by the square root of our sample size, which means this 12 will have about 0.91 added and subtracted to it. So my interval is 11.09 to 12.91. Quick side note about this distribution. The sample, we weren't given the data, so we couldn't look at the distribution of the data, but it's definitely skewed, because if you look at the information we are given, the center of the distribution, or the balance point of the distribution, was 12. The standard deviation is 18. If it was normally distributed, 95% of the data would be within 2 standard deviations of the mean, which means I would have 95% of my data between -24 and 48, which makes no sense when we're talking about the number of books that are read. So it's definitely skewed to the right, and that's okay because the sample size was large enough. So we just kind of ignored that fact. We didn't have to find what the distribution looked like. So now I'm going to go ahead and conclude this. We are 95% confident, which means we have created this in such a way that 95% of samples created like this, or samples found, would have an interval when created like this that captures the mean. So it's not 95% probability, but 95% of this process will end up being correct. So that the interval from 11.09 to 12.91 books captures, again, the mean for our population, and then in the context of what we're talking about. So that's actually creating it. There is a question that's a follow-up question for this one. Part B says, they reported that adults read 14 books in the previous 12 months. Do we have evidence that it's something different than that? So looking at this interval, remember, these are the plausible values for what mu could be. Is 14 a plausible value for what mu could be? No. So because it's not a plausible value, the question is, do you have evidence that it's something different than 14? Yes, we do. We have evidence that it's different because 14 is not in the confidence interval. So 14 is not a plausible value for the number of books read by Americans in the previous 12 months. So that's the nitty-gritty of how to actually calculate this. As always, your calculator would love to do this for you. So let me find my camera again. Again, sorry, Casio and Inspire, Learn to Google. But everybody else, if you go to the same place we found our other tests, so second distributions. That's not where we found our tests. I lied. Go back. Stat, and then tests. You're going to see the 1-prop z-test that we've used, the 2-prop z-test. If you scroll down, you'll see the 1-prop z-interval. We are looking for a t-interval because we just made an interval and we used it with a t process here. Now I know we're calling it 1 sample t-interval, but that's how your calculator has coded it in. It's going to ask if you have data or stats. Did we just put a list of data into L1? Heck no. We have stats. We have what is calculated off of this. So we were told that the average of our sample was 12, standard deviation was 18 from a sample of 1,520, and we were trying to find the interval for 95% confidence interval. So I'm going to hit calculate, and we get basically the exact same thing. This gives us a little more decimal values than what we rounded to, but we still got 11.09 to 12.91. This will sometimes be different depending on intermediate rounding. So if you ever are just going to hop to this step and not show your work, make sure you're saying using a calculator. But as always, still list things like this is what I got for my degree of freedom. Here's what I used for my X-bar. List out everything out that you're doing. But you are more than welcome to check your work this way. Example 4 is on here, and I think I was intending for you to do this one on your own, so I'll have it on the answer key that is posted later. I do want to point out that this one's a little bit different. Unlike the last example, it doesn't just say, oh, the sample mean was 14, but it gives you the sample data. So not only can you come up with some type of sketch of the distribution to be able to tell if it's plausible to be normally distributed, when you go to find X-bar, you are going to have to calculate it, which kind of sucks, but sometimes life sucks, so get over it. So you can find X-bar, you can find S, you can calculate your interval from that. You'll be checking your answer at the end. Just a little bit of review though. We talked about this when we did the confidence intervals for proportion. So just to go back through the changes in margin of error. So for example, the margin of error can be decreasing, which means you took your point estimate and you added and subtracted some number to come up with your confidence interval. It's possible to have that be a smaller thing you add and subtract if your sample size has gone up, which kind of makes sense. The thing we're adding and subtracting has a sample size in the denominator. So if you're wanting this overall number to be smaller, then divide by a bigger number and make the whole thing smaller. So mathematically, that's what's happening here. The margin of error excuse me, is proportional to 1 over root n. So if I quadruple the sample size, so if I take this exact same expression and instead of n, I squeeze in a 4 in here, we know the square root of 4 is 2. So I'd go back to the exact same thing, but there would be a 2 that I'm dividing by now. So it's going to cut our margin of error in half, as long as nothing else changes. The margin of error will be larger for higher confidence level. If you have to have a greater capture rate, you're going to have a wider interval in order to achieve that. And as always, this has nothing to do with bias in your sampling method. It is only sampling variability that you are creating this interval for. So if somebody designs a biased sample, like that sucks, you're just going to have a bad interval based off of it. You're not taking that into account whenever you add and subtract your margin of error. So this better work when I upload it. Email me questions. A bunch of you have been, which is awesome. I'm trying to make things clear on the calendar, so read all the stuff that's on the calendar before you email me. If you have specific questions about, I don't understand example 3, or I did this question, I don't understand it, I'm trying to answer them both to you, in addition to putting a frequently asked question on the class calendar. There was one for Unit 8. There will be one for Unit 9 as well. It's somewhere on the calendar already. Go look for it. If you find your question there, awesome. If you have additional questions, awesome. Email me if you cannot find the question on your own. I know the AP test has been changing. I don't know what they've been sending out to you. But if you are planning to take the AP test, it is now going to be an at-home assessment. It's going to be 45 minutes long, and it's going to be completely online and completely free response, which I don't know how well that's going to go. It's kind of weird. They've clearly never done this before. Whatever. So if you're still wanting to do that, just know that that's how they've changed things, which is why I'm trying to change the My AP practice to be giving you those types of questions rather than the multiple choice. And then I'm just going to lean on Khan Academy to give you more of just the basic multiple choice type question practice. You do need to join the Khan Academy class because that is part of the requirement of showing that you're going through this material. Anything that is designated as a practice that gives you a score. The score gives me feedback on how you're doing, but your grade, no grade anywhere will be affected by that number. So it's just kind of feedback for you and for me. It's not going to harm you if the Khan Academy practice is crappy. Once you do join the class, if you're not seeing your practice, you basically just need to wait for me to update the assignments. I don't know why they have it like that. It doesn't update until I tell it to update. So sorry if you're waiting on me. I'll try and check that as soon as I can. Excuse me. The only thing that is going to affect a grade are the unit assessments. Those unit assessments, Unit 8's already up there. They're going to always be Google Forms so that it can be graded quickly. They're always going to be multiple choice because life's hard enough for me to make these videos for you, let alone find time to grade things and have you submit whatever. It'd be a pain. So I'm just not doing that. So instead, they're going to be multiple choice. And those of you who are wanting to get Lewis and Clark credit for this class, the dual credit, your grade will be affected by these tests. So while everything else is like, hey, I did it, and it doesn't matter that I have no idea what I'm doing, it will only if you're trying to get that dual credit. It is possible to drop your grade in the dual credit part of the class. It is not possible for your AHS grade to drop lower than it was the last time I saw you. So that will not go down. It can only possibly go up with the extra credit that you might have done last week. But again, the Unit 9 starts everything that is required, and the Unit 8 test is for sure 100% required. I don't recommend taking the Unit 8 test without doing all the Unit 8 work, but you do you. Email me questions.